R is very small, the potential energy is very, very big. But it's above the x-axis. There's below the x-axis. What does it do in between? It dips. So it descends rapidly here, and then it dips, and it comes out of the dip, and it asymptotically tends towards the x-axis. It doesn't ever get there.
So when we had to say that forces with the forces potential energy rises.
Yes.
And then attractive forces.
I wouldn't say. I mean, it's
It's
no. Look, decreasing potential energy means an repulsive force.
Yeah.
Which is decreasing.
Oh.
So a decreasing potential energy creates repulsive forces. Whereas an increasing potential energy, like over here, you can see it's coming up, and here it's going down, meaning decreasing. So decreasing potential energy creates repulsive forces. Increasing potential energy, like over here where it's coming up, creates attractive forces. So yeah, these are equilibrium. This is a repulsive force. This creates repulsive forces. This creates attractive forces. Okay. Good stuff. Take that away. It's not really part of the picture. Okay. It's just two things you have to learn about this. There is a sweet spot here. Do you see? They attract each other, they get closer, they get closer, they get closer, but if they get too close, they start repelling each other. So there's a sweet spot. There's a zone somewhere in between where they don't attract or repel. There's a sweet spot where the force of attraction and the force of repulsion are equal. Does that make sense? The attractive force and the repulsive force are perfectly equal in the sweet spot. This is the sweet spot here. The bottom of the dip, that's the sweet spot. That is where these two atoms will stop coming back and forth. Shh, shh, shh. Can I keep going? There's a sweet spot here. Do you understand the idea of a sweet spot? It's like Goldilocks, not too hot, not too cold. That's just right over there. Now, that lowest point is the sweet spot. That is where the two atoms will sort of come to equilibrium. They'll stop being attracted or stop being repulsed or just stay there. Now, we have to learn some labels for this. At the sweet spot, there's some labels. The depth of the sweet spot is called the bond energy. Right? That's the depth of the sweet spot. From the x-axis to the dip, that's the bond energy. The radius of the sweet spot, you see the radius is the x thing? The radius of the sweet spot is called the bond length. Correct. Now that's where, because the two atoms will settle in the sweet spot, it means that that's where they'll stay. So if you look at two bonded atoms, they will be this far apart. That's why it's called the bond length. Because that's how far apart two bonded atoms will be since the one sticks in the sweet spot. And the reason why this is called the bond energy is because that's how much energy the bond has. Look, it can have zero energy, but it dips down into the sweet spot to have that amount of energy. So that's the bond energy. Yeah, we'll communicate on the group. Cheers. Okay. Now, bond length, bond energy. Does it make sense why it's called the bond energy? Because this is the energy we're measuring here. So the amount you need for a bond is this. Now, the only important principle here that you need to know, which is in your study guides, you can go read about it, is that bond length is inversely proportional to bond energy. Do you understand this symbol? It means inversely proportional. In other words, as bond length goes up, bond energy goes down. That's basically what that means. It's not quite the meaning of inverse proportionality, but pretty close. Okay, so I'm going to take away these two headings because I want to draw another curve in red. Okay. Now, I'm going to draw another curve. I want this curve to represent a substance with a bigger bond length. In other words, I'm just going to draw the same curve, but with bigger bond length. Okay? Or I could just imagine it's the same substance, but it hasn't got to the sweet spot yet. It's still getting there. So the bond length is longer. Something like that. Okay, what will it look like? Bigger bond length. So here's let's think this. I want a bigger bond length. In other words, I must draw it over here. Do you agree? That's bigger. So here's my original bond length, because it corresponds to the sweet spot. I want a bigger bond length. Now, if I want a bigger bond length, I need less. If I want a bigger bond length, I need less bond energy. Now, how do I draw less bond energy? It means my dip mustn't be as low as this, because the dip is the bond energy. So if I have less bond energy, less bond energy, it means my dip mustn't be as much. Does that make sense? So I'm going to have a longer bond length, but a longer bond length. So instead of that bond length, I'm going to make it longer into that bond length. But that means that instead of this bond energy, I need to make it smaller. To not as to start there and make it less of a dip to smaller bond energy. So let's draw that picture. Still starts up here. So that's this one. I need to have my dip here, but it needs to be. So I'm going to make my dip there. Why am I putting it there? Well, it's further away, so the bond length is bigger, but it's not quite as far down, so the dip is smaller. So I'm satisfying both of the things that I want. So it's you've got to still start here. Let's think. It's going to look like this. Okay. And they're not supposed to touch, by the way. I don't have enough space, but you must imagine that they never touch. But can you see this part of the drawing? Also there, no touching. Let me just take it away. There you go. That's good enough, I think. You see, they don't touch. You must imagine over here they don't touch, and over there they don't touch. Now, well, there you go. Do you see why this is different? This one has a bigger bond length than that one, but it has a smaller bond energy than that one. That's exactly what we stated happens. So over here is the black bond energy and the black bond length. And over here is the red bond energy, and over there is the red bond length. You see, longer bond length, smaller bond energy. So if you want to draw two different pictures, that's how they must be different. The one must have a longer bond length but a smaller bond energy than the other. And of course, I could just, to show you, I could also do the same thing where I make a smaller bond length with a bigger bond energy. Yeah, it's not the best curve, but you understand what I'm trying to show. It needs to be a little bit dip here. There you go. Do you see the shorter bond length now? Shorter bond length and a bigger bond energy. Yeah, there you go. That's how that picture works. Okay, we're done. That's the whole lesson. Yay!